just like we have linear momentum for translational motion, we have angular momentum for rotational motion. Consider the torque. Torque equals I alpha, and alpha is delta omega divided by delta t. Delta omega is the change in the angular velocity, so it's omega final minus omega initial. So now we are dealing with I omega final minus I omega initial, divide that by delta t. We define the angular momentum as the product of I omega. Just like linear momentum, P equals mv. Rather than I, you have m, and rather than omega, you have v. So here for angular motion, rotational motion, the angular momentum is I omega. Okay? So the net external torque is equal to the change in the angular momentum per unit time. If there is no change in angular momentum, then the net external torque is 0. Okay, this is very much similar to the equation that we have earlier. Force equals delta P divided by delta T. If delta P is 0, no change in linear momentum, then the external force is 0. That is the situation that we used to analyze collisions, as you recall. It turned out that this is very important conservation law that help us to solve the problem and to understand the physics of rotation better. So wherever delta L by delta T is 0, the angular momentum is conserved. The angular momentum is conserved and the net external torque is 0. That is the condition to have the angular momentum conserved. Okay? When delta L by delta T is 0, then the net external torque is 0. This means L initial is equal to L final. The initial angular momentum for the system is equal to the final angular momentum for the system. So now we have three conservation laws. We have the conservation of mechanical energy, the conservation of linear momentum, and the conservation of angular momentum. These conservation laws are applicable when you have an isolated system. Okay, an isolated system, a system that you isolate from its surrounding. So these quantities remain constant. This is one example that we are familiar with. You have on ice skating, you will see the dancers there changing their spinning speed by simply changing the spread of their arms or their legs. If you compare this situation to that situation, here the moment of inertia is much less than the moment of inertia here, because this is an extended object, extended arms and extended legs, so the moment of inertia is higher. This system is isolated from its surrounding, so the angular momentum is conserved. By changing the geometry, by changing the status of the arms and legs, increasing the moment of inertia will decrease the speed, will decrease omega, and bringing the arms and the legs closer, as in this situation, will decrease the moment of inertia. Increasing the moment of inertia will increase omega, the spinning speed. As simple as that. So you have I initial, omega initial equals I final, omega final. The system is isolated. So the dancer on the ice will continue changing the spinning speed by just spreading the arms and the legs or bringing them closer. Example: a student sits on a pivoted stool while holding a pair of weights The stool is free to rotate about a vertical axis with negligible friction. The moment of inertia of student weights and the stool is 2.25 kilogram meter squared. The student is set in rotation with arms outstretched, making one complete turn every 1.26 seconds. Arms outstretched. What is the initial angular speed of the system? As he rotates, he pulls the weights inward so that the new moment of inertia of the system, student, objects, and stool becomes 1.8 kilogram meter squared. What is the new angular speed of the system? Find the work done by the student on the system while pulling in the weights. Ignore energy lost through dissipation in his muscles. This is a nice example to illustrate what we just learned concerning conservation of angular momentum. So omega equals 2 pi f, and f is 1 over t. So from the given information concerning the period, we calculate omega, divide 2 pi by period. The period for one rotation, we are told, is 1.26 seconds. This is t, the period for one rotation. So from this information, we know the initial value for omega. Now, the system is isolated from its surrounding, no friction there. L initial equals L final. That is to say, I initial omega initial equals I final omega final. So I initial 2.25 and omega initial 4.99. I final is 1.8. We have omega final, one unknown in this equation. We solve for omega final. It is 6.24 radian per second. Okay, so as you see, he was able to increase the angular speed by simply bringing the arms inward. So this way, reducing the moment of inertia, this led to increasing the spinning velocity. Then we take the change in kinetic energy. This is equal to the work done by the student. Change in kinetic energy, half I final omega final squared minus half I initial omega initial squared. We substitute for I and for omega. Evaluate, the work is 7.03 joules. If global warming continues, it's likely that some ice from the polar ice caps of the Earth will melt, and the water will be distributed closer to the equator. If this occurs, would the length of the day, which is the length of one rotation, increase, decrease, or remain the same? So in this case, we need to consider the conservation of angular momentum. If more mass moved toward the equator, this means the moment of inertia will increase. If the moment of inertia increases, since the angular momentum is conserved, this means omega will decrease. If omega decreases, then the period will increase, because the period is the reciprocal of omega. Okay, so the day will get longer. We are done with this chapter. In this chapter, we learned about torque as the physical quantity needed for rotational motion. You cannot get any angular acceleration without a net external torque. We learned how to calculate the torque. We learned how to calculate the center of mass coordinates. We learned about the conditions of equilibrium. Sigma f is 0 for the translational equilibrium, and sigma tau equals 0 for the rotational equilibrium. We learned about the rotational second law of motion, tau equals I alpha. So the net external torque is equal to I alpha, and I is the moment of inertia, sigma mr squared, and alpha is the angular acceleration, which is related to the translational acceleration by this formula. Translational acceleration equals R alpha. Then we learned how to calculate the rotational kinetic energy. It is half I omega squared. And we learned how to apply the conservation of energy principle to solve problems. Finally, we learned about angular momentum, L, which is equal to I omega, and we learned about the importance of this angular momentum. It is conserved when the net torque is 0. By having the angular momentum conserved, this means L initial equals L final for any spinning system, and this is very helpful to solve problems.